Okay, everybody. So we're going to start Module 7, which is a new probability distribution. It's called the chi-square distribution. And we're going to show you first how closely it's related to the normal distribution for a hypothesis test that is one you've done before in what we call a binomial experiment. This is just when we were working with categorical data. With categorical data fall into categories, and when there's two categories, we call it binomial. If there's more than two categories, we call it multinomial. So the chi-square distribution is for working with categorical data usually, whether there's two or more categories. So we're going to go ahead and jump right in here. It says, in this lesson, we consider multinomial experiments. In a previous optional lesson that we skipped, you may have learned about binomial experiments. Multinomial experiments are like binomial experiments. There are n independent trials, but instead of 2 outcomes per trial, success and failure, we allow 2 or more outcomes per trial. The binomial experiment is a special case of a multinomial experiment. We begin with a binomial experiment in the context of a hypothesis test for a single population proportion. Okay, so the context is about asthma incidence among youth. The Statistical Abstract of the United States reported that in 2008, approximately 17% of male youth were told they had asthma. A researcher in Florida wants to compare this to the proportion of male youth in that state who have asthma. In a recent random sample of 400 male youth in Florida, 88 responded that they had asthma. This sample is the result of a binomial experiment. Each trial has 2 outcomes: asthma, success, or no asthma, failure. At the 1%, and so it's categorical data, there's 2 categories. Okay. At the 1% level of significance, we will investigate the claim that asthma among male youth in Florida is different from the national figure, and that was 17%. Okay, so this is a hypothesis test about a single population proportion P. What are the appropriate null and alternative hypotheses? Well, like I say, it's nice to start with the alternative hypothesis, and they're saying that the proportion of male youth in Florida with asthma is different, that is not equal, from the national figure, which up above, remember, is 17%. P is not 17%, is what they're saying. And so the null hypothesis, of course, that has to be P equals 0.17. So we've done this hypothesis test before. Okay, now, as before, there were criteria for normality because we're going to use the normal distribution on this, and that is that the expected number of successes, NP, has to be at least 10. Also, the expected number of failures, n times 1 minus b, has to be at least 10. So the expected number of successes, NP, is, if you look back, there were 400 male youth, so that's n, times p, which is 17%, and so we're just doing 17% of 400. Turns out that's 68, and of course that's greater than or equal to 10. And the expected number of failures is n times 1 minus p. So, of course, n is still 400. 1 minus p is 1 minus 17%. And the idea is that if 17% of male youth in Florida have asthma, then 83%, which is 1 minus 17%, 83%, don't have asthma, theoretically. Okay, that's 332. And of course, this is also greater than or equal to 10. So we've satisfied both criteria, so the criteria are met. Okay, are they met? Yes. What's the sample proportion? Well, p hat is always x over n. X is the number of successes. So if you go back, there were 88 boys in Florida that had asthma, so it's 88 out of 400. And that's 22%, 0.22. And of course, that's pretty different from 17%. The claim is that in Florida that the rate is different from the national figure. So this is looking pretty reasonable, but we have to see how many standard errors the difference is before we can consider it more than just kind of a chance variation. Okay, so at this point we would take our z-scores. So you can see the formula up there. So p hat minus p over the square root of p times 1 minus p over n. So again, this is something you've done before. Our p hat was 22%. And if you look back up above, the null hypothesis says that p is 17%. So 22 minus 17% for p. And then coming down, 17% for p, and then 1 minus 17%. And then over n, which was, I think, 400, boys. Okay? And so you do the math on that, and I would encourage you to pause the video right now and see if you can compute this, and come back when you've got it. Okay, so when I did it, now notice it says to keep 5 places after the decimal. So when I did it, I got 2.66217, super precise there. The precision is to make a point. We have to do a p-value. Okay. And just as a reminder, we have a p-value calculator in Desmos. Now this is the normal distribution. So remember, we're working with z-scores this time, not t-scores. We can label our z statistic here 2.66217, and then we want this area here so that we can use that for the p-value. Okay, so I'm going to jump over to Desmos real quick and see if we can figure that out. Okay, so now I'm signed in, and I'm going to load in my normal distribution p-value calculator. And so all you have to do is put in the z statistic. You may remember we got 2.66217. Oops, I did it wrong. 217. Let me show you that. Okay, so you can see that tail down there in the graph. And the area, if you look, it's 0.003882. 0.03882. Oops. Oh, goodness sakes. I get it. 0.03882. That is not the p-value because, as they say down below here, this is a two-tailed test, so we have to double the area of the tail. I'm just going to go with the 0.00388, double it, and so that comes out to be 0.00776. Okay? And it says, what do you conclude about the null and alternative hypotheses? Well, the p-value is 0.00776, and we're comparing that to alpha. So if you go back, you can see at the 1% level of significance, we're testing this claim. So that's 0.01. And remember, compare two digits for two digits. 0.01 has two digits. Look at 0.00, which are the first two digits of our p-value. And of course, 00 is less. So we can say that the p-value is less. And that means we reject the null hypothesis. And we support the alternative hypothesis, which had said that the proportion was different from 17%, and that's what we're going to support. So the data support the claim. And if you like, you can pause the video and write in your own conclusion here, and then come back. I'll put my conclusion in. Now, so the data support the claim that the proportion of male youth in Florida have asthma at a rate different from the national figure. Oops. At a rate and the national figure is 17%. Okay. So that's just sort of a review. Nothing new there, but just want to show it as a refresher. But also, this again is our binomial experiment, and what we really want here is a way to expand it to a multinomial experiment. And there's just lots of times where you're gathering categorical data and there's more than two outcomes. You know, yes, no, maybe you could just have yes, no, but what if it was yes, no, or maybe? That might be three outcomes, and certainly a reasonable kind of a question to ask if you're gathering data. So we're going to jump right into this next part. Okay. So, under next steps, it says the z-statistic in the previous example works well for binomial experiments when there are only two outcomes per trial. When there are three or more outcomes per trial, things get more complicated, and the z-statistic doesn't allow for sample proportions for more outcomes. When there are two or more outcomes per trial, we can use a different test statistic. Now again, two outcomes we just did, which was either you have asthma or you don't. But what about more outcomes? Well, again, you can use a different test statistic in those cases. The statistic is denoted, now that looks like an X, but that's a Greek letter that we pronounce chi, and usually spelled CHI. Okay, and the letter, the distribution is called chi-square, not just chi, but chi-square. Okay, you will understand why it's chi-square shortly. The formula for the test statistic that we're going to be computing is this. Now, we just call the variable chi-square. You're actually not squaring something. Okay. There is something squared that comes into it, but you'll see that when we get there. Okay, so what you have to do is sum the observed number of outcomes in each category and subtract the expected number of outcomes in each category. So the expected outcomes are just the average number of successes and the average number of failures. If the null hypothesis is true, those are your expected outcomes. The observed are what actually happened. So anyway, you subtract observed minus expected, you square that, and you divide by the expected. Add this up for every category for your variable, and that's your chi-square statistic. Okay, so it says each outcome corresponds to one term in the sum above. E stands for expected frequency, and O stands for observed frequency for each possible outcome in the experiment. All right, so we're going to run this on the asthma problem that we just did. So it says for the asthma incidence among male youth example, each sample member falls into one of two categories. Either the teen has asthma or not. So for the teens with asthma, give the observed and expected frequencies. So A, what's the observed number of teens with asthma? So these are the successes in the experiment. So the teens with asthma, if you go back to the original problem, it said that there were 400 kids and 88 had asthma. Okay, so that's the observed number of what we're calling successes, 88. Okay, and I think I want to jump down for the kids without asthma. Okay, how many were observed there, kids without asthma? Well, there were 400 boys. 88 had asthma, so if you subtract that, you get 312. That's the number of boys without asthma. All right, let's go back up. Now, the expected frequency is always n times p. You're just taking 17% of 400 here, so NP is the formula for expected frequency. And so, again, it's the 400 boys, and we need 17% of them. Why? Because the null hypothesis said 17% of boys have asthma. And that's what we expect. If it's true, 17% of what? 400. So we're just doing this computation. And it turns out 17% of 400 is 68. So that's what we expected under the null hypothesis. But what did we get? 88. On question C, it says the expected frequencies is based on the proportion p from the null hypothesis. Is it similar to the observed frequency? Okay, you can put whatever you think. I think 68 is pretty far from 88, so for me the answer is no. Okay, and of course there's not a right answer here, and I'm not even going to try and justify it. Now, remember the formula for the chi-square statistic. We have to sum this term, O minus E squared divided by E, for every category of this variable. So you can see the O and the E up above. Let's just do this. O is 88 minus E, that's 68. So we'll subtract that, and by the way, that's 20. And if you square 20, that's 400. And then you have to divide by E again, which is again 68. Okay, take a moment. Go ahead and pause if you like, and figure out what this part of the statistic is. Okay, so I got 5.8824 with 4 places after the decimal, as it says. Oops, 24. Okay? So that's the part of the chi-square statistic for the kids with asthma. Now we have to do it again for the boys without asthma. So on question 8, we've already done this. We have to give the observed frequencies anyway we've done, but not the expected frequencies. So what's the observed number of teens without asthma? Those are the failures in the experiment. Again, there were 400 boys altogether, 88 with asthma. 400 minus 88 is 312. Okay, so we got that. Now, what's the expected number of kids without asthma? This is the mean number of failures, which is n times 1 minus p. And again, I'll run you through this. N times 1 minus p is 400 times 1 minus the 17% that do have asthma. And remember, 1 minus 17% is 83%. Okay, so if 17% of boys have asthma, then 83% don't. And so the question is, how many do we expect without asthma? Well, 83% of the 400 boys. So you just multiply that out. Feel free to pause. And you should have gotten 332. So that's the expected number of boys. Now, to me, when they ask in C, the expected frequency E just computed is based on the proportion P from the null hypothesis. Is it similar to the observed frequency? Well, 332 does seem a little more similar to 312. It's still a difference of 20, but it doesn't seem like such a big difference when the numbers are so big. So I'll say it's more similar this time. Okay, just like that. Now we have to do that computation for the chi-square statistic again, so I'm going to just kind of zoom out a little here so we can see the O's and the E's. So the first observed frequency was 312, so we're going to, in D down below, we're going to do 312. Oops. minus the expected frequency, which was 332. So you square that and divide by the expected frequency again, which again is 332. Okay. Feel free to pause if you like. Okay, I got 1.2048. Okay, we're going to add those up. There's a question E here, which I'm kind of interested in. It says, think about the test statistic where expected frequencies are based on P from the null hypothesis. Here's the test statistic, this chi-square statistic. Now this is difficult, but listen. It says if the null hypothesis is false, what would you expect the statistic to be, small or large? Okay, so here you go. The null hypothesis is false, which means the frequencies that we expected, the expected frequencies here, would be really wrong, meaning they should be really different from what's actually happening in reality. So if the null hypothesis is false, the expected frequencies should be pretty different from what we observe. And so when you subtract them, that should be a big number, okay, because the difference is large. When you square it, it gets bigger, okay? And so this gets big when the null hypothesis is false. So the answer is large. Okay? And actually I'm going to make this into a sentence. Chi-square is large when HO is false. Okay? Now that just tells you when the null hypothesis is false, the statistic goes to the right. Okay? When it's true, the statistic goes to the left. That just means this is going to be a right-tailed test always. So there's no left-tailed test and there's no two-tailed tests. Okay. So on question 9, it says the number of, so we've nailed down the fact this is going to be a right-tailed test. So on question 9, it says the number of observed teens with asthma was observed from a random sample and varies from sample to sample. Once this value is known, that is the number of kids with asthma, is the number of teens without asthma random? No, it's not. Okay. The number of teens without asthma had to be the 400 kids minus the 88 with asthma. So it's not random. The 88 kids with asthma, you couldn't have controlled how that would have come out. But the second you knew there were 88 kids with asthma, there had to be 312 without. So only one of these values is random. Okay, so the question of degrees of freedom is arising because of the fact that we've got a collection of observations, but they're not all random. So it says if degrees of freedom represent the number of observed frequencies that vary freely or randomly, how many degrees of freedom are present among the two observed frequencies? Well, there's only one that's random. DF is 1. Okay, the observed teens with asthma is random. Okay, but not those without asthma. Okay, strange, but that's, again, this degree of freedom issue, and we're going to be constructing a probability distribution for our statistic. And distribution width is always sort of determined by the amount of randomness in your statistic. So you have to have some sort of measure for the randomness, and of course that's the degrees of freedom. Okay, so now this is just a summary of everything we've got. I believe the observed number of kids with asthma was 88, and there were 312 without asthma. Okay, only one of those was random. Now the expected frequencies, if you go back, for the kids with asthma, it was this number, the 68. Okay, that was what was expected. And then, where was the kids without asthma expected frequency? That was this 332. Okay. And then the contribution to the chi-square statistic. So the first time we did that, we got this 5.8824, which I'll paste down here. And then for the second time, the kids without asthma, the contribution to the chi-square statistic was this 1.2048, which we'll paste down. Okay, and then we have to add that up. So take a sec. All right, so I got 7.0872. And they're telling me to keep 3 places after the decimal down here. So the chi-square statistic, that's this thing, the sum of O minus E squared over E here. So that came out to be the 7.0872. Okay, so now we've got our chi-square statistic 7.0872. What we want to do here is tie this result to the original hypothesis test that we looked at. So in question 13 it says, in this question we begin to understand the relationship between the z and chi-square test statistics for the same hypothesis test. So here it says compute the square of the z-score from question 3. So let's go back and find that. Here we go. So it's 2.66217. I'll copy that. But again, we want to square this, so let's write 2.66217 squared. And it says to round 3 places after the decimal, and when you do, you see you get 7.087, which is the same as this one for chi-square, 7.087. So you see the chi-square distribution statistic is actually the square of the z statistic that we got. So it says, how is on question 14, how is the chi-square statistic with 1 degree of freedom related to the z statistic? Well, simply put, the chi-square statistic is the square of z. Okay, so this is why we call chi-square, because it's related to squared z-scores. All right, let's go ahead and read the you need to know. This one's a little tough. So it says, and by the way, this is with, I should mention that when there are 2 outcomes, this is a binomial experiment, meaning the kids either have asthma or they don't. That's a success or a failure. 2 outcomes of the categorical variable. When we do the chi-square statistic, the 2 parts add up to 1 z-score. So even though there's 2 outcomes, they make 1 z-score. And as we go forward, you'll see, of course that's the degrees of freedom issue. There's 2 outcomes, 1 z-score. If there are k outcomes for the categorical variable, then it turns out to be described by distribution of the sum of k minus 1 squared z-scores, k minus 1, because only k minus 1 of these are random values. Okay, so here we go. When conducting a multinomial experiment with k outcomes per trial, the chi-square statistic varies approximately according to the chi-square distribution with k minus 1 degrees of freedom. With 1 degree of freedom, the chi-square distribution is the probability distribution of squared z-scores from the standard normal distribution. With k minus 1 degrees of freedom, the chi-square distribution is the distribution of all sums of k minus 1 squared z-scores, randomly selected. There are only k minus 1 of them because there are only k minus 1 random values in our statistic. Because of this, the distribution only allows non-negative values because you're squaring z-scores. Several chi-square distribution curves are plotted below with varying degrees of freedom. Okay, so as we say, the chi-square distribution is only for positive values because it represents the squares. And so 2 degrees of freedom, 4 degrees of freedom, and so on. Okay, and you can see that it sort of ends up being almost a bell shape, but it's skewed to the right for sure. It turns out if your degrees of freedom gets big enough, it approaches a normal distribution. Okay, the chi-square hypothesis test which we're conducting is always right-tailed, as I've said already. So the p-value is the area to the right of the test statistic. The chi-square distribution with 1 degree of freedom, which is what we're doing right now, is plotted below. The graph is quite strange looking. As you can see, it kind of has a spike here and it goes up forever. The area shaded to the right of the test statistic represents a p-value. Take some time with your instructor to learn how to find such p-values using technology. Okay, so what I want to do here is I'm going to refer back. First of all, we need to get this this chi-square statistic. So I'm going to do the 2.0872 that we've used here as our chi-square statistic. Remember, it's 1 degree of freedom. And if you get onto Canvas, I've put in on the top with the p-value calculators. If you go into that, you'll see there's a chi-square distribution calculator down there on the bottom. So just go into that, and this will launch Desmos. Okay, and then you just have to put your numbers in. We've already decided that this had 1 degree of freedom. And let me zoom out on that. There you go. And then our chi-square statistic we'll put in here. I think it was 2.0872. Oops, there's a problem. I think that's it. Okay, and so this is our statistic here. P-value, something's wrong. I don't think it's 2.0872. It was 7.0872, my bad. So we'll go and fix that. Okay, that's better. So you can see there's a little sliver on the distribution just to the right of 7 that's shaded. And you can see the p-value down there, 0.00776 is what I'll copy over. Okay, and then let's just make a note for later reference that the p-value calculator is on the Canvas homepage for this course. And so you can jump in there. And now it's asking us to compare the p-value that we got in question 4, which is a completely different set of computations. So you can see Let's go way back to question 4. Here we go. And this is for the z-test, not the chi-square. But notice the p-value here is 0.00776. It is identical to what we just got. Okay, so the p-values are identical. And so any conclusion that we would have done with one hypothesis test would always be the exact same conclusion for the other hypothesis test. If the p-values are the same, you're always going to make the same decision. So if we use a 1% level of significance, what would we conclude about our original null and alternative hypotheses? Well, as before, the p-value is 0.00776. Look at those first two digits. It's 0.00, which is less than 0.01, and that's our alpha value. And with it being less, we would reject the null hypothesis and support the alternative. Okay. Same conclusion, and so it's just a different way of doing the test with this chi-square statistic here. Turns out it gives the square of the z-score when there's only 1 degree of freedom, so you'd expect, these are very, very closely related tests. Let's do a quick conclusion here. It says, in summary, because the z-test for a population proportion yields the same p-value as the corresponding chi-square test with 1 degree of freedom, the tests are equivalent. So why use a chi-square test? The answer is because it allows more than 2 outcomes per trial. The z-test statistic only works for binomial experiments with 2 outcomes, but the chi-square statistic can be applied to multinomial experiments where there are more than 2 outcomes per trial. Okay, we will investigate examples of this in our next lesson. All right, that's it for this one. Feel free to go back and replay anything that you missed or didn't understand, and I can take questions in my office hour or in class. I'll talk to you guys later.